So in the previous lecture, we have discussed about atomic packing factor for BCC and FCC, and we noted that for BCC the APF is 0.68 and for FCC the APF is 0.74. Now let's talk about hexagonal close packed structure today. Now first of all, let's find out number of atoms per unit cell. For HCP, number of atoms per unit cell for HCP. So let us consider this arrangement. So this is a HCP unit cell. And let me show the reduced sphere representation. Of atoms. So atoms are situated at these lattice points, and there are 3 atoms situated inside the unit cell, as we understood earlier. Now to find number of atoms per unit cell, we have to consider the sharing of atoms. So let's first consider the atoms which are situated at the corner. Right, so this particular atom is shared by how many unit cells? Okay, so let me draw a quick representation over here to understand the sharing of atoms. Let's say this is one unit cell. Okay, besides that there is one more such unit cell over here. Okay, besides that there is one more such unit cell. Okay, so if the atom is situated at this corner, so we can say this particular atom is being shared by these 3 unit cells, as well as there will be 3 more unit cells on the top of this. Like this. Okay, so let me quickly represent it. There will be 3 more such unit cells available over here, 1 and one more over here, that should be parallel to this. Yes. Okay, so that means this particular atom is shared by 6 unit cells. So I can say that inside one unit cell we have 1/6 of the atom. Inside one unit cell we have 1/6 of the atom. So how many such atoms are there? 1/6 into, so 1, 2, 3, 4, 5, 6 and 6 more, 1, 2, 3, 4, 5, 6. So that means we have total 12 such atoms. Plus, now if we consider this center atom, face center atom, so let's say we have one face centered atom situated over here. So how many unit cells are sharing this particular atom? 2 unit cells only. So we can say this is 1/2 of this atom inside this particular unit cell. So we have 1/2 into, how many such atoms we have? 1 and 2. So we can say 1/2 into 2. Now any atom remaining? Yes, we have 3 full atoms inside this unit cell. So we will say plus 3. So this gives us 2 plus this gives us 1 plus this gives us 3. So that means we have 6 number of atoms. Then 6 atoms we have per unit cell. So we will say number of atoms per unit cell will be 6. So this will help us to find the total atom volume, and we will use this for finding the APF. Now other than this, there is one more important calculation required if we wish to find APF of HCP, and that is relation between age length and height of unit cell. Because for HCP it is not like a cube. For HCP this is age length A and this is the height of the unit cell C, which is different than this. So both are different. So we should have some relation between these two. Okay, and then the relation between age length and the radius of atom. Then we will be able to find numerical value of APF. So now let's find this relation between C and A, that is height of the unit cell and age length of the unit cell. So for that, let us consider this portion, this highlighted portion of the unit cell. Okay, so that means I am considering this cell. So let me draw it over here. Let me consider this highlighted portion. Okay, but now what about the atomic arrangement for this portion? So we can see over here that atoms are situated at each corner. So we can say we have atoms at each corner, atom at this corner, atom at this corner, atom at this corner, and likewise we have this arrangement of atoms. But also, if we see this cell, this hexagonal unit cell, we have 3 atoms inside the cell. If we look at repetitiveness of this cell, the highlighted cell which we have represented over here, if we look at the repetitiveness of this cell, we can see that we have 2 more such unit cell but with some different orientation. So we can identify that there is one more cell like this over here, right, and one more cell is over here. That way we can identify. So if we say that we have these 3 cells of same dimension but with some different orientation, and inside the cell if we have 3 atoms, then we can say that each of this cell contains one full atom. So if I represent that atom on this figure, I can represent it somewhere over here, one full atom inside this cell. Now if I connect this atom to these atoms, so that forms a tetrahedron. So the arrangement is such that that forms one tetrahedron. Now if I give some notation to this, let's say this is atom J, this is K, this is L, and this is M. And if I draw this separately, I can represent it by this figure. So I will say that this is J, this is K, this is L, and this is M. Now if I connect center of this face, this triangular face, to M, so that can give me this arrangement. Let's say this point is represented by H. So now I can see that I have this triangle J H M triangle. Also now I have, as this is a tetrahedron, I have triangular faces. So out of this triangular faces, let me consider J, L and K. If I draw this separately, that would be like this. So let's say this is J, this is K, and this is L. Now the H point would be somewhere over here. So let's say this is point H. If I connect point H to midpoint of JK, so that will be, the construction will be like this, and this will be 30 degree. As this is a regular tetrahedron, this will be 30 degree. Also, from the previous figure, we know that the edge length is A. So here we can consider this is A, right? So for this figure we can say This is A by 2. As we have connected point H to midpoint of J and K. So if JK is A, then we can say this is A by 2. Correct? Now, considering this triangle, as this will be 90 degree. So considering this triangle, we can write JM square is equal to JH square plus MH square. Now what is the value of Jm? As this is a regular tetrahedron, if Jk is A, this would also be A. So we can write A square is equal to JH square, so we don't have this value, plus MH square Okay, now can we represent MH by something else? Yes. Again, let me show the previous figure. We have said that the total height of the unit cell is C, and these three atoms are situated at C by 2. Right? So this distance MH is nothing but C by 2. This distance is C by 2. So in place of MH square, I can write C square by 4. So we know that Jm is equal to A, JH we don't know, and MH we already know that it is C by 2. So we can write A square is equal to JH square plus C square by 4. Now from this triangle, if we consider this one JH and N, we can write cos 30 is equal to A by 2 divided by JH, which is equal to root 3 by 2, and from that we can say JH is equal to A by root 3. Now if we put this value of JH in this equation, then what we can write is A square is equal to A square by 3 plus C square by 4. So that gives us 2A square by 3 is equal to C square by 4. You can say C square by A square is equal to 2 into 4 divided by 3, which is equal to 8 by 3. Right? And so we can say, from this we can say C by A is equal to under root of 8 by 3, which is equal to 1.633. So this is the relation between C and A, which is required for calculation of APF, atomic packing factor. So from this we can always write C is equal to 1.633 A. So let's end this lecture over here, and in the next lecture we will continue derivation of atomic packing factor for HCP unit cell.